Okay, good evening, everyone. This is lesson 5. This is our last all team lesson, and then the plan is to have individual meetings with each team over the next couple of weeks or so, once your rocket is finished and you've submitted your flight readiness review document. And we'll just basically talk through your rocket, not necessarily in the order in which you wrote it up, but perhaps just like top to bottom, and make sure as best we can tell at a distance that it's in good shape. So at the end of this call, I'll be probably going around the room and just seeing if any groups are prepared to suggest a time slot for that meeting. Could be anytime, literally in the next 2 weeks, and I suspect if you're not done with your rocket, you probably shouldn't schedule it for tomorrow. So we'll get back to that. The other thing I want to ask you, and so I'll ask you now, and then I'll perhaps ask you again, is if weather cooperates, are you willing to go out on the first weekend of December and try and fly these things? I'm not perhaps going to require that. I do hope that all these teams do fly their rocket, but I will, if I can, try to arrange for a flight opportunity at the end of the semester or close to the end of the semester, but only if there's interest. If nobody's going to show up, then I won't do it. So we'll return to that. Okay, looking at my my notes, I've posted already homework and vocabulary / concepts for this lesson, and I'm just have those printed in front of me. You might want to open those up. And I think I'm just going to, well, actually, let me start with the homework. So there are a few more, almost the last chapters actually of the Rocketry book. I'd encourage you to look those over. And I hope you paint your rocket. You may or may not paint it before you fly it, but I would encourage you to paint it. I see Sophia has her rocket here and it's not painted yet, but hopefully that will change. On the other hand, I didn't provide you with any paint at all. So if you're going to paint your rocket, you'll have to look into that and don't get in trouble. Frankly, my students more than once have gotten themselves in trouble by painting in places on my campus where they should not have done. So my preference is to paint outside, although at this time of year that can be challenging. So figure it out. And then as far as homework exercises, remember that you should be working on your open rocket model. That's something that we will talk about. In fact, I should, maybe this is mentioned, maybe this is not, but I should definitely collect your open rocket model when you turn in your flight readiness review. And remember, one of the things you want to do is weigh the rocket and make sure that the weight agrees with the model. And if it doesn't, fix the model so that it is realistic. Similarly, balance your rocket. It won't have a motor in it, but see where its balance point is located, and then push things around in the model so as to make the weight and the balance point both match the real rocket. And then once you put a motor in it, hopefully you'll be able to predict fairly well how it will perform. And then at the end of today, we'll try to at least start a discussion about time slots for these checkout interviews. And then your flight readiness review document, I want that submitted at least 24 hours before your checkout so that we have a chance to look it over before we have time to talk to you. Of course, that should be with the rocket in place. You could even do it in person if you're willing to come here. We could do those in person, but I'm expecting mostly to do those by Zoom. Make sure that you're there and with the rocket. And so this might not be a Tuesday evening if that's not a time that you can collect all your people together and be in the location where the rocket is located. As far as building, again, looking at the homework slide, you have a sled to finish up. Sophia will talk about her sled today. And then final tweaks. That's much of what this particular presentation is about, or what are some of the final things that need doing. Even if you are completely up to date and have your rocket basically done, there are still some final tweaks I haven't told you about. We'll do some calculations, and I'll show you where to and how to do those for ejection charge sizing and delay grinding and upper rail button location and things like that. So that's the homework document. I had in mind for the lesson that we would essentially talk our way through the vocabulary, because I kind of have written it in the order in which I wanted to talk about things. But before I do that, I'm going to ask Sophia what she would like to tell you or ask you, maybe ask you about your rocket build and tell you about her rocket build, and then we'll return to my tweaks and extra stuff. So here is Sophia.
All right. everybody. So I have gotten a couple emails throughout the week just about questions with your build. So I wanted to check in and see how everyone is doing so far. So like last time, we can start alphabetical order. So we'll go with Augsburg.
Yes. Yeah, in terms of build, we pretty much have everything going. We're kind of in the stage where we're building the electronics bay. We're still trying to piece that together, and we're letting the epoxy sit on for the fins on the base of the rocket.
Great. All right, and then Bethel.
We're still pretty far behind, but we've been spending time in RockSim just to get an idea of how the rocket's gonna work before we put too much together as a team, because this is our first build still.
So are you using RockSim or are you using Open Rocket?
We're using RockSim because we had bought it before we had gotten on these Zoom calls.
That's fine.
Okay. All right, and then Sentry.
We're still just finished the internal fillets, and then everything else is pretty much done besides gluing the fin can and actually attaching the rail button first.
Yes.
But most of it's gone pretty smoothly.
Good. And then what's next? Fond du Lac.
Oh, we got a couple fillets to go. Got the fins on. We're working on designing our sled right now, and that's what's going on.
Nice. All right, and then Hamlin.
We have almost everything built. We're just working on the electronics stuff right now.
Great. And then Inver Hills.
We're currently working on the fillets for outside fillets for the fins, and I think we're also working on the sleds. Otherwise, everything's going smooth.
Good. And then UMD.
We're currently finishing up the fin can, as well as we're working on getting the shock cord connected to the nose cone.
Cool. And then Normandale.
So Joe, if you're
Anyone?
talking, we're not
Yeah.
hearing you.
Oh, sorry. Today we put our fin can in, and we just started designing our electronics bay. So
Nice. Sweet. All right. So it looks like a lot of people are on the electronics portion, which is great because I'll talk about that today. And hopefully tomorrow I can put more in our slides to kind of show how I physically went through all those steps. I thought it'd be a little bit better to talk through it with you guys before I went ahead and assembled everything. So
let's do that first. The things that I have are tweaks that can wait. Let's talk about what your electronics bay or av bay looks like,
yeah,
where the things are going to go, and how the wires actually work. And hopefully everybody has received your altimeter in the mail. I mailed those out and they were supposed to be delivered before today. If you haven't received yours, look for it. And if you can't find it, maybe then we should talk.
yeah. So I was able to cut my avionics bay, and if you've looked in the slides in the last like hour, you'll see it's in there, and it's nothing fancy. I literally just took.
So take a look at what the view is seeing. It's not
Yeah.
anything in the hands yet.
Yes. So as you can see, it's literally just a piece of scrap wood that I found at the bottom of the barrel. So it's, I think,
So you didn't put ABCD on it?
no, I did not put ABCD. I don't know where those letters came from, but this was free, so I took it. So as you can see, it's just like a thin piece of wood. So this will be where my actual electronics are mounted to. It fits, I think it's 11.5 inches by 2.7 inches. So it's made to fit pretty much within the middle of the coupler airframe assembly. And then you can see, I know last time we mentioned how we attach this sled to the actual threaded rods. Some ways are you can use tubes. I've seen people zip tie them. Here I just cut out tabs. I laser cut out tabs. So the holes are the same diameter as the threaded rods. And this, I just used wood glue to glue it back onto the sled itself. And so as you can see, here are my threaded rods and my bulkhead, and I just slide it right on. Like that. And then I'm able to slide the next bulk plate on pretty easily. And wow. Eventually this will make its way into my coupler assembly. But yeah, you can see it's not too fancy, but it's enough to get the job done.
And there won't be any sliding around in there, right?
Right.
Once it's sealed, it will be tight.
Yes, and so, you know, we only have a battery, and our altimeter and maybe a camera. So obviously this seems like a lot of space, but it's just so there's not a lot of slop between the two bulk plates, and we can keep everything in place and avoid any sort of shaking. But yeah.
And then can you tell them what will be on the outside? You haven't glued it or mounted it yet, but the outside of your two bulk plates.
Yes, so then on the outside of our bulk plates, obviously, on the actual sled here, we'll have our altimeter and our battery, but on the outside, we will have our actual ejection charges, which is what we want to go off. So that's where these two things come into play, your terminal block, as well as the little C PVC caps. And so, as you can see, I marked places to put future items. As you can see, there's a circle. That's where I will put the cap. And that's what will hold my ejection charges once I've made them. And then I also have a square where I will put my terminal block on the outside here. And you can see the little dot next to it that I made. And that's where I will have to drill a hole, which will ultimately be where I can form the connection between the stuff going on inside the avionics bay and then my ejection charges on the outside. So I'll be able to put my ejection chart, my wires for my altimeter through that hole into the terminal block that I'll have here. And the terminal block will also have connections to my ejection charges that are in this circular cup.
And so essentially the wires that penetrate the bulk plate will stay in place, at least on the top side. On the bottom side, you have to take your bulk plate off. And so those wires have to be able to slide in and out.
Right.
But ultimately, if you wire this right, you can set it up so that you don't even have to open up your avionics bay necessarily. We probably will, but you don't necessarily have to open it up. You can just replace the ejection charges completely from the outside.
Mm-hmm. Right.
And then what about, well, go ahead with the actual wiring. In particular, I'm curious about the switch and things like that.
So if you have gotten your AIM altimeter, you'll see it looks like this. So we have a blue terminal block down here. There's positive and negative terminal, as well as just a blank cell. So I already have it wired up now. You can see I have my battery with the red and black wires, and then my switch is actually the purple wires here. And you can see my battery goes to negative, and then one goes into the blank cell. And then I put the one end of my switch into the blank cell and the other into the positive terminal.
So ultimately, the battery has to go between the positive and the negative. It turns out the thing in the middle is not electrically attached to anything. So you can just use that as a terminal block. And that's handy because that terminal block will allow you to add the switch without having to do any soldering.
Right.
On the other hand, you will actually have to do some soldering to, you might have to do some soldering to attach the battery holder to the altimeter, maybe. So you didn't, but
I didn't.
Frankly, if had you used that,
the clip,
the clip properly, you would have then soldered wires. And
right.
so, okay.
Yeah, and
then remind us about ups and downs for the battery.
Yeah, so you should place it. So it should be oriented up.
Nope, 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 nope. The battery terminals need to face down in your rocket.
Okay. My bad.
You can put your battery above or below your altimeter. That doesn't matter, but the battery itself essentially needs to be upside down within the rocket, so that when the rocket accelerates, the battery gets pressed more firmly into the battery holder.
And we can also kind of simulate what would happen on the launch pad. So right now I have my battery wired into my altimeter, but you can see nothing's happening, nothing's beeping. That's because my switch is turned off. But turn it on.
I can spend it.
But if we turn the switch, if I can get it.
So she's just turning the screw switch. This switch will be on the outside of your rocket, so you can reach it even after the rocket is sealed up.
You see,
Okay, so if you can hear the beeping, that will be a pattern from this AIM Extra, and you need to memorize what the pattern should be. And Steve put a question, does this altimeter care which way is up? And the answer is it does not. This is a barometric only altimeter, so it needs to be able to sense changes in pressure, but it does not have any accelerometers. So unlike a Raven, this does not have an up and down side on the altimeter. You could place it lengthwise or even sideways in the rocket as long as it will fit.
Okay.
On the other hand, tell me what you have in there right now. It looks like you have some LEDs or something.
yeah, so in my altimeter right now, there are LEDs instead of ejection charges. So like on one end, we have the terminal block for the battery and the switch. Here is for our drogue and main chute. So as you can see, when I turn the switch on, they light up to show continuity.
They light up just a little tiny bit.
Just
They
a
shouldn't,
tiny
they
bit.
shouldn't light up a lot, otherwise that would fire the charges by mistake.
Right. Yeah, so, but you can actually, one cool thing is if you plug this into your computer, so
Can you actually do that?
I can actually do that.
Okay, so last week we showed you, not too effectively, the Raven software. The AIM Extra has software. It's more basic than the Raven, that's okay. And so what Sophia is going to do is share her screen and show you what the I'm sorry, not AIM Extra, AIM USB. AIM Extra is a different product. What the AIM USB software looks like. Be a little bit careful when you plug in things. You probably know this anyway, but when you plug in USB cables, that you don't shear off the USB holder. That would be a bad day. So a quick question right now, is your thing powered or not right now? And does it matter whether it's powered or not right now? Eventually it will need to be powered, right?
Right.
But right now, it doesn't matter. You're just getting your software up and running, yes?
Mhm. Yes.
Okay, so here's what I'm going to do. I'm going to keep this camera on your hardware, but why don't you share your screen? And show us what you're seeing on your computer.
Okay. So right now it's not very interesting. It's just a purple screen. But if you can go to open. And so I actually just downloaded the entire software file from the AIM USB website. And part of that came with actual data from real flights. And so just opening up this one, we can see the flight data. So we have altitude and velocity. And something we can actually do is go to tools and control device and emulate launch. And here we do actually need to connect the battery. So right now I'm just turning the switch on. So there is power going to the LEDs. And so here it's just doing the initial beeps that it does at the beginning of a launch. And so now it's actually launching, or at least it's following the data to show that it is launching. And once it gets to the altitude, the ejection charge will go off. And that's when we'll see the drogue. So launch was detected.
So
Their chute goes off.
one of the LEDs got bright, and then is the other one going to go a few seconds later?
Yeah, so then the other one is the main chute, which is supposed to go off at a specific altitude. It happens a little later, so we might have to be patient to see it. Yep,
There it went
it
out.
is.
That's cool.
Yeah. And then after that, it's just following the rest of the flight until it hits ground.
So if you close that window and point out on the graph, where are the two ejection charges?
So here the colors are flipped, but our blue LED was right here where that red bar is, which is right around apogee. And then the blue bar here is where that red LED went off, which is where our main chute was to be deployed.
And just by looking at the shape of this, can you say that this was a dual deploy rocket flight?
Yes.
For instance, it came down at one speed with one slope from
Oh,
apogee down to main. And then after the main fired, then it came down slower, more slowly, as if it had a second chute. And presumably this is data from a real rocket flight. And notice you can also see some spikes, especially around the deployment of the main chute. That suggests that pressure is going up inside of the av bay. When you fire a nearby explosive, for instance, that just means their av bay wasn't totally tight.
Something else you can do from this window here is obviously simulate flights, but you can also adjust the data set or settings within the altimeter. So if you want to have a specific delay in, so maybe you don't want your ejection charge to go off right at apogee, you want it to go a few seconds after. If you have some sort of redundant ejection charge system, then you would use this window to change that, as well as adjust. So line B here is our main chute line. So here you would select at what altitude you'd want it deployed at, and if you want any sort of delay. You can also calibrate the device at that point. Yeah.
So it turns out that the default values, which are there, say fire line A at apogee and fire line B at 150 meters above the ground. Those are both fairly reasonable values, even for what we're trying to do, just as long as you have a flight that goes at least 150 meters. You are allowed to change the units, but I think if you change the units, it only changes some of the units, and that 150 still has to be in meters. So if you want 500 feet or 700 feet, you'll have to convert it to meters, and then this is where you would put it into the software and then write the settings. So read settings means tell me what the device thinks it wants to do, and write settings says, tell the device, this is what I really want to do. So after you write the settings, you might want to read the settings and make sure that it got it. If you close that and go back up to that tools menu and go to control device. Here is where you can actually ask the device, what is the pressure right now? Okay, and what is the voltage right now? And now hold up the device in front of the camera and then press the button that says fire 2 seconds. Aha. So in other words, both of the LEDs went off for 2 seconds there. Consider that another kind of a test to make sure this thing is working. Okay, so the wiring is pretty basic, but it's very important that you get it right. And we will be watching and checking and asking questions in our checkout interview just to make sure that we're all happy with how it went. Again, this is a pressure altimeter, so it does not care which end is up, but it also means you can't have a totally sealed avionics bay. because it won't know what is the external pressure. Anything more right now, Sophia?
I think that's about it. I'll have detailed pictures of how I do the terminal blocks and the caps tomorrow. Just wanted to be able to explain everything beforehand.
Okay, great. So here's what I want to do now. I want to step quickly through my vocabulary, my notes, basically, and just make some comments. So my recommendation is that you prime your rocket before you paint it. Maybe that's not totally necessary, although if you're using fiberglass or plastic materials that are really hard for paint to stick to, that is kind of important. That you scuff your rocket, and then you prime your rocket, and then you paint your rocket. In this particular case, the place that you're going to have the most trouble with is the nose cone. If you decide you don't want a black nose cone, but some other color, you'll have a hard time perhaps getting the paint to stick to that. But if you scuff it and then prime it and then paint it, you'll have better luck. Upper rail button. So the rail buttons should be, the lower rail button should be sort of as low as is practical. And the upper rail button really ought to be at the center of gravity, or certainly not below the center of gravity. So you kind of have two options with this rocket. It's likely that your center of gravity will be somewhere in the lower section of the rocket, and that's where I would actually prefer to put the lower rail button. You can reach inside the thing or find someone on your team who has small hands and reach inside and place the rail button there, make sure it's really, really well aligned with the bottom one, sticking out, glue it in place, and then place the two rail buttons very much axially aligned. Another option is, can you pull out a rail button? Someone's asking what they look like. Well, we'll show you in a moment. Another option is to put the rail button on the upper section of the rocket, perhaps low on the upper section, like within the coupler tubing. And the advantage of that is that you can actually twist the two sections of the rocket with respect to each other and get them to line up. So you don't have to align them and glue them in place, but rather glue one in the bottom, put one in the top, and then just rotate it until they line up. That's okay. In fact, some people prefer that, but often that's not at the center of gravity. Okay? So, Sophia, why don't you show us what a rail button looks like? I'll just spin this around towards you again. Just hold it up in your hand.
Yeah, so the rail buttons come in their own separate little baggie in the kit. And the rail buttons have three parts. So there's the weld nut. So there's the flat portion here that will be pressed up against the inside of the rocket.
That goes inside the airframe.
Right, which is
It's
why,
sticking out.
yeah. So if you look in the slides, I show, or I say epoxy should go right on this ring, which then you can put it in through the inside of the rocket. And then, so this little barrel will be sticking out. You put this black button over the top.
That's the button. That's the rail button.
Yep, and then you have a screw to hold it in place.
And I think there's a bevel on the screw, and so there's probably a bevel on the button. So it's possible to put that in the wrong way around.
That is correct.
And then you want it to spin. You want it to be able to roll on the rail. So you don't want to actually tighten it down too much.
Mhm.
And if, in fact, the only way to keep the screw in there is to tighten it down, then perhaps you should just use some glue or something in the threads to make sure that the screw goes in the right amount and doesn't go in too tightly. Question in the chat, how do we find the CG? And the answer is use your model. Make sure your model matches the actual balance point. So you can find the CG, by balancing the rocket in your hands, make sure all the pieces are there, except for the motor. And then make sure your model agrees with that. And then, of course, when you add your motor, that will move the CG down somewhat. So I would suggest perhaps place the rail button where the CG is, even without a motor. And then anytime you add a motor, you will always be slightly too high, and slightly too high is okay. Just never want to be lower than the CG. Okay. So basically, you'll more or less calculate and place your upper rail button. That's the very last thing, literally. You want to finish the rocket and make sure you know where it balances and where the CG is, and then pretty much decide where to put your upper rail button and make sure it lines up with your lower rail button. What about the parachutes? Well, here is a rocket. And so you'll place one parachute along this piece of recovery harness. And so my recommendation is that you just literally put a loop inside of the harness, right like that. And then you can put a quick link on that, and you can put your parachutes in your flame protectors on that. The key is to make sure that when it hangs from that loop, the upper part of the rocket here doesn't strike the lower part as they both dangle. So in other words, this loop is likely to be pretty close to the avionics bay. Okay, not in the middle, because if it's in the middle, then the two pieces will clang against each other for sure. Okay, and then the other part, here is the nose cone, and here's more recovery harness. And in this case, you want to put a loop in here somewhere. Again, not in the middle, but just to make sure. This is in fact where the main parachute, so it'll dangle from this part. Ah, there, no. Okay, so this one doesn't have a loop in it. I could choose, and I think I would probably choose to put this loop fairly high, so that the nose cone doesn't strike anything below. So here it is. I just put a knot in there. So there's my loop, just like that. And I'm ready to put my quick link right on there. So in both cases, the loop needs to be thoughtfully placed, and it will be placed probably fairly high. Just think about how the thing hangs down. It first hangs down under a drogue parachute, and then the main parachute will dominate. So it really hangs down mostly under the main parachute, and try to keep the pieces that are dangling from hitting each other. It can't be avoided when you first open up. Sometimes they hit each other, you can't avoid that, but at least while they're falling and drifting down under parachute, you don't want them to be hitting each other over and over again. Okay, let's talk about separations. So I just took that rocket apart. Let me go back to that rocket. And point out that the avionics bay stays with the upper section, okay? So the first thing that I want to happen during a flight is I want the lower section to separate from the avionics bay, okay? So if I were to stuff all this stuff back, there would be a parachute in here as well. So what I'm doing is easier than in actuality. Let me just put this rocket so it looks right. Okay, so there's the bottom. Let's see if I can get the top in. I just added a bunch of cord to this. This is not the best way to do it. I'm just trying to get it out of the way. Thank you. Okay, so here's the rocket. So in flight, I want this to come apart, but not this to come apart, okay? So the way I keep the upper part from coming apart is I'm going to use rivets. We've given you some rivets, and so rivets require you to drill a hole that goes through the airframe and through the coupler underneath it, and then place the rivet in, and the rivet will hold them together permanently until you pull the rivet back out. The rivet will have two pieces, the part that sticks through the hole and the part that sticks into that part to splay it open, okay? So there is a gap that will be riveted closed right there. This, on the other hand, I just want this to be a friction fit. In other words, I want that to come apart if I pull on it or if I shake on it, but not to be so loose that it just drops off gravitationally. I definitely want an explosive charge in here to be able to get this off relatively easily. And so if yours is very tight, make sure you do some sanding, maybe add some talcum powder, baby powder, something like that to get this to come apart, because this is what's going to get the drogue chute out. That's the most important separation, frankly, during the flight. And we'll have two chances at it. One chance is your explosion from your avionics. And the second chance, which is in the same part of the rocket to pressurize it, is the motor eject, which is 1.3 grams, which is likely to be more than you think you really need. But if yours didn't work, it's always good to go for more. So there'll be two explosions here, perhaps not simultaneous, both of which are just trying to get the tail end off the rocket and get the drogue chute out. Now that we're dropping with the rocket like that, underneath the drogue chute. Now it's time to sense that we're getting close to the ground and blow the front end off the rocket. And in that case, I mean the nose cone. So this also can't be tremendously tight. But one problem is if you shock the rocket back here with an explosion and drogue chute, the nose cone will almost for sure pull right off inertially. Okay, so what we're going to do is we're going to put shear pins. Shear pins in some sense are breakable rivets. They're mini rivets. So you'll screw in here. So a shear pin, which is a nylon screw, will go in through the airframe and then into the nose cone. And then when you pressurize this part of the rocket with your second explosion, you will literally break the shear pins and drive this thing out. That's what we'll actually practice. We're going to do an ejection charge test on your rocket on the ground and make sure you can actually get your nose cone off to get the main parachute out. But we'll also need to, at least in our hands, check that this particular connection is not too tight so that we have confidence that we can get the rear end of the rocket off as well. So we won't check that with an explosive charge on the ground. So the friction fit goes at the bottom of the avionics bay. The rivets go at the top of the avionics bay, and the shear pins go on the shoulder of the nose cone. Now, that's for the separations that you want. There are some separations that could happen that you don't want. One of these is called drag separation. So it turns out that there's parts of the rocket that will drag more than other parts in flight, especially the fins. So there will be more drag on the lower part of your rocket than on the upper part. And if you don't have a good enough friction fit, the lower part will get dragged off the upper part. That's why your friction fit has to be reasonably tight. You can blow it off, but it won't just fall apart. Okay? So to avoid drag separation, you want to make sure that you have a pretty good friction fit. But there's another thing that might drive your rocket apart, and that is just the pressure itself. So the idea is there's pressure, there's air inside of the rocket, and if the rocket is pretty tight, as you fly up and go into a lower pressure part of the atmosphere, the inside air will have a tendency to push the pieces of the rocket apart. This can actually push apart the bottom from the avionics bay from the top. Anything that's shear pinned or riveted together, I won't worry about. But the bottom section, which is just a friction fit, I might worry a little bit that that could actually have internal natural pressurization separation. And so the way I'm going to combat that and recommend that you combat that is actually to drill a very small hole somewhere in that bottom section. Call that a bleed hole. That just lets any excess pressure kind of slowly get out. I don't want a gaping hole because I'm going to pressurize that myself in a minute. And I want to make sure my pressurization actually does something and doesn't just go out the hole. So we'll probably add a small bleed hole somewhere in the bottom section. I usually add it high in the bottom section right underneath the avionics bay. But we've already mentioned a couple times that the electronics that requires you to know what is the actual pressure outside of the vehicle, like the AIM USB for sure, and also the altimeter 2, which you might have as on a data logger, that does require that you essentially vent the area. So this means putting specific static portholes or vent holes both into the AV bay and also maybe into the nose cone if that's where you might have your altimeter 2. So this particular rocket already has essentially holes for all of these things. So for instance, right here is a hole for a rivet, and right next to it on the collar is a hole that is venting the avionics bay. It's handy to put that on the collar so that when you slide things together and apart, it doesn't inadvertently cover that hole. So there's one, there's one, there's one. There's actually 4 holes so as to vent this avionics bay. There's even a 5th hole, but that hole is actually for the screw switch. So that wouldn't necessarily be open. Also, if I look up higher, here are holes for shear pins. They might be a little small to see. And then here are holes right here, right here, right here. These are holes to actually vent the nose cone so that this thing could fly with like an altimeter 2 pressure sensor inside the nose cone, and it would be familiar with what's going on outside. So notice there's a lot of holes in the rocket, and they're all placed thoughtfully. In fact, there should be one more hole. Let me see if I can find it. There it is, right there. There's a hole right there. That's my bleed hole. That's the bleed hole. It's below the avionics bay, which comes down to here, right below it. I like to put that high so that it doesn't get covered by a parachute. The parachute will tend to slump down to the bottom, but it could cover the hole if the hole was way down here. Of course, it has to be above the top of the fin can and the centering rings down there. So there's a hole. That's a bleed hole for this bottom section. Okay, holy moly, we got lots of holes in that thing. Let's talk quickly about, well, here's a question, and that is how to calculate the size of the holes. And the answer is, I don't actually calculate the size of some of the holes. The bleed hole, I usually put a maybe 1/8 inch hole. That should be adequate. When it comes to the static portholes, there is a formula, and the formula, which is in the book, says something like calculate the volume that you're trying to vent in cubic inches and divide by 400. It's a rule of thumb.
Oh,
for the static
main?
portholes.
Yeah.
Okay, divide by 400, I think.
Yeah.
And then that should be the diameter of a single hole if you only make one. My recommendation is that you make more than one. My recommendation is that you don't have one hole for venting high and another hole low, lest air goes in the high hole and out the low hole, and you get actually wind literally inside of your avionics bay. If you're going to put several holes, that I do recommend that, put them around the same height of the rocket. So that particular rocket had 4 holes, and they were sort of spaced all the way around the collar. It's usually not problematic to have more vent holes than you need, but you definitely need to make sure that you have enough area that formula, look it up in your book, that formula proposes so as to vent the 60 or whatever cubic inches. In fact, we could calculate it, the number of cubic inches inside of this avionics bay. I think in your slides, you already had a proposal of what would be the size of the vent holes. And I don't know if you did that with a calculation or if that was given to you in the instructions, or you used the formula. That's great. Okay, so there is a formula. It's a very simplistic formula. Okay. On the other hand, we also need to figure out how much gunpowder, literally, or gunpowder substitute. We'll probably use Pyrodex, which is a gunpowder substitute. How much charge to put into our charges to pressurize the av bay. I'm sorry, not the av bay. No, don't pressurize the av bay. Sorry, to pressurize the part below the av bay, get out the drogue, and above the av bay to get out the main. So let me show you how that could be done. Share screen. So I've posted the following calculator. Let's go find my own copy of it. It's called, where is it? There it is, Simple Ejection Charge Calculator. Okay. So Sophia, we're just gonna eyeball this. So I've got a calculator here, and the calculator first says, how much volume are you trying to pressurize? So you should have a tape measure. You don't, no problem. You do know the diameter of your rocket, Sophia. Tell me, what is the diameter of this rocket?
It is 3 inches.
So it's a 3-inch diameter rocket. And approximately how long is the section of the rocket that you're going to pressurize at the bottom there? Just with your hands, just see if you can guess. Is it 12 inches? Is it 16 inches? Approximately how much of the rocket is to be pressurized? And so this is the distance from the bottom of the avionics bay to the top of the fin can. So from here to about here, right? Or is it the top is here?
Top is around here.
Okay, so I'm going to hazard a guess that that's 16 inches.
Yeah.
You need to do this properly, but if we have a 3-inch diameter and 16-inch long volume, that means we have about 113 cubic inches that need pressurization. This is in the bottom section, okay? The yellow things here will self-calculate, and the blue ones are places where you can put in your own parameters. I would suggest 15 psi as an appropriate overpressure. So in other words, we want to pressurize that from 1 atmosphere to about 2 atmospheres. which then would provide about 106 pounds of force pushing down on the rear of the rocket. Hopefully that is plenty of force to overcome your friction fit. And so it suggests that this requires a little bit less than 1 gram, 0.88 grams, okay? If I go a little bit farther down, there's actually another calculation in the high power rocketry text, and that calculation gives 0.86 grams. It's essentially the same as mine. Now, Sophia, we're going back to the top section, okay? The top section is a significantly smaller part, right? Okay, so basically, of that top section, some part of it is occupied by the nose cone and some part of it is occupied by the av bay. And so the part that remains to be pressurized is only about maybe 6, 8 inches long. Let's go with 8 inches, okay? So that's fine. So here's what I'm going to do. I'm going to say 3-inch diameter, 8 inches. And so now it says, oh, you only need 0.44 grams, less than 0.5 gram. But remember that this section of the rocket is actually being held together with shear pins. And each shear pin requires about 35 pounds to break. And so if there were 0 shear pins, then 0.44 would be the answer. But if I put, for instance, 2 shear pins, which also need to be broken, it almost doubles the amount of powder. So now I'm up to 0.73 grams for the upper section. And then it turns out that if I'm using Pyrodex, my recommendation is that you increase that by about 15%. Pyrodex has the same energy basically as black powder, as gunpowder, but it doesn't burn quite as thoroughly. So I believe that for this rocket, 1 gram, less than 1 gram, both in the upper section and the lower section is likely to be okay, but you should do the calculation more exactly. And notice down here it says, oh, by the way, how does this compare to 1.3 grams? Because that's what's built into the motor eject. And the answer is it's way less than 1.3 grams. That's fine. We're going to try and blow it apart with 1 gram or less. And if that doesn't work, well, we'll try with 1.3 grams on the motor eject. That definitely should open up the bottom section. So here is how to calculate the amount of powder you need. I will handle the black powder. I will handle the Pyrodex and provide you with what you need for ejection charges, first for a ground test and then for a flight test. But you need to do the calculation and request the appropriate amount. Okay, fine. The last 2 pointers on my list of vocabulary: igniter versus E-match. So basically an E-match, an electronic match, is something that you apply electricity to, and it will make a spark. And if that E-match is buried inside of black powder or Pyrodex, it will cause it to ignite. On the other hand, you also need to get the motor lit. And so the motor lighting is done with what's called an igniter. And depending on who you talk to, it used to be that igniters were big and E-matches were not. And nowadays they're about the same. In fact, they might be exactly the same. And the reason Cicerone in particular can get away with it is, remember inside of the motor, there's that little plug. That little plug is essentially pressed black powder. And if you can get even an E-match, which is sort of wimpy, right next to that piece, you can actually get your motor to light. So these days, E-matches and igniters are not necessarily that different from one another, but you might have to buy igniters separately and E-matches separately. E-matches will be used for ejection charges, and igniters are sold specifically for starting motors. And each motor will come with one, but if that one fails to light it, you might have to, or I might have to buy extra ones. I will be providing the E-matches for the ejection charges for this thing. Question from Inver Hills: when would you like the calculation? And the answer is on the day of. It would be fine. We're not really supposed to make up these things in advance, so pretty much you tell me on the day of, I want 0.9 grams and 0.75 grams. And I will probably say, I might round that to 1 and 1. But anyway, and then I will provide you with the powder and the E-match on the spot. So this will be done on the day of the flight. You should do the calculation in advance to make sure that you know how, but I don't actually need the numbers in advance. And I will sort of know what to expect because Sophia has a rocket and she will be asking me in advance about what. So I'll kind of know how to double check your calculations. The last thing I have on my list is the delay grain. Remember we talked about that a motor, a Cicerone motor that ends with an A means adjustable. So like a -12A means 12 seconds from burnout to motor eject explosion, not launch to motor eject explosion, from burnout to motor eject explosion. And then A means adjustable. So you can actually take the 12 seconds and grind it down. In other words, remove some of the material, make the flame front proceed more quickly. And so this is where your simulation comes. Your simulation will tell you, here is what I propose. Here's the best delay for this rocket. It's one of the things in the table. And so frankly, if you have a simulation and it says, best delay is 9 seconds, that's okay. We'll start with 12 seconds and we'll remove 3 seconds to get it down to 9. On the other hand, if your simulation says 17 seconds to apogee, this is not the right motor, because this motor can only last 12 seconds before it explodes. And so that shouldn't happen to us. Pretty much my expectation is you will reach apogee before, possibly well before, the motor is ready to explode, and we can adjust the motor accordingly. But how are you doing, Sophia, on your model? Have you played with it or not so much recently? I'm going to ask Sophia to confirm, and I think this is true, that this motor will be completely appropriate, and we might grind it down and we might not grind it down. Here's why we might not. If it turns out that it should reach apogee at 11 seconds and the motor is built for 12 seconds, 1 second after apogee, that's not the end of the world. In fact, we're going to try and fire our charges at apogee, and I'd kind of like the motor eject to go off later than our charges. And so that I can even see 2 puffs of smoke in the sky. It's like boom, boom. That was the first one. That was the second one. And the first one, or maybe the second one, was what actually broke the rocket. So I might allow us to go a little bit past apogee if necessary, but definitely 3, 4, 5 seconds too long will definitely shorten up the motor eject so that it goes off at a more appropriate time, slightly after apogee. Definitely, I don't want it to go off before apogee when I'm still climbing. That would be a bad idea. Okay, so that's all we've got, except that we want to talk to people about ideas. And if you aren't really ready to talk about this, so be it. But I'm going to remind you that I had suggested that we should, sorry, one moment. Second here. Okay, I had suggested that we try to schedule these things essentially sometime in the next 2 weeks approximately, from like tomorrow through a week from tomorrow, which is the day before Thanksgiving, to a week after that, which is the first Wednesday of December. Doesn't have to be on a Wednesday, but I would be interested to hear from any team. How about I not even call on people, but just ask people who is ready, willing to talk about specific dates and specific times of days, and I will start looking at my schedule. Anybody? These are for our checkout interviews.
I guess I can go for Augsburg. I think ideally from our team is mostly available for Monday around 3.
So you're thinking about like Monday, November 29th?
That's correct.
I can do that. And Sophia, rather than limiting us to when you can and I can, how about I take the ones I can, and if you can join us, fine. And if you can't join us, so be it. Just curious, 3 p.m. on a Monday or no?
4 p.m. works for me.
Augsburg, would you be willing to do 4 p.m. instead of 3 p.m.?
Yeah, that should be an issue. I'll double check with them, but yeah, that shouldn't be an issue.
That will just allow Sophia to be with us. Okay, so I have one for 4 p.m. on Monday, November 29th, Augsburg. Anybody else? It's probably prudent to give yourself some time to get your stuff finished. But on the other hand, I can't have everybody on Wednesday, December 1st. We'll run out of time. Bethel, have you talked about this at all? Century, anybody? not hearing anybody. So either everybody has not talked about it or everybody is muted.
I'll have to talk my team until I can get back to you on that. Sorry.
Okay, I will take proposals by email. Let's get this sorted out this week. I mean, I'm not saying let's have the scheduled meetings this week, but I really would like to have all these meetings on my calendar before the end of this week. Okay, so Century, I'll hear back from you. Anybody willing to propose a time even right now? Or let me at least get clarification from everybody that you're going to think about it and going to get back to me this week. So Inver Hills, you're going to get back to me this week,
Yes, we will.
but not right now.
Nope, not right now.
That's okay. Duluth,
Yep, same thing. We'll have to talk about it. We'll get back to you later this week.
okay. Normandale,
Yeah, we should be able to get back to you by Friday.
okay, please do. First come, first serve, obviously. Hamlin,
We will get back to you before the end of the week.
fine. How about you, Steve Fond du Lac?
Yeah, we'll have to do some calculating and thinking too.
Okay, and let's see, who did I not explicitly ask? Bethel, maybe?
We'll get back to you this week.
Okay. So, fine, I've got one on Monday, the 29th. I would say Monday, the 29th, Tuesday, the 30th, Wednesday, the 30th, or the 1st of December. Those would be the obvious times to do it. And I could probably get all 8 of these in on those 3 times, with the exception that I'm busy mostly Tuesday afternoons. That's when I teach a once a week class. So I actually come to this meeting Tuesday night right after that class. But this time, Tuesday night, could possibly work, but only for one team. If anybody wants to grab that time slot right now without even talking to your team, that would be okay. But otherwise, I will expect to hear back from everybody over the next couple days, definitely before the weekend. Any takers for Tuesday night at 6:30? Okay, remember that we want you to work on those slides, that flight readiness review set of slides, just to make sure you have thought through the things that we want you to think through, and that you can send us that document at least one day, 24 hours in advance of whatever your scheduled time is. And send us a copy of your Open Rocket or RockSim, either one, model, so that we can discuss how that worked out, especially if we try to run it and have some questions or issues about that. Last question, and that is, if I arrange a flight opportunity on the first weekend of December, that would either be Saturday the 4th or perhaps Sunday the 5th of December, and I'm not even choosing which one because it's weather dependent. But I would go for the 4th if both days were good, but either the 4th or 5th of December. Augsburg, would you show up?
Yeah, we would.
Bethel, would you come?
Probably not.
Century?
Most likely not.
Fond du Lac?
We'd want to, yeah.
Hamlin, what do you think about a December launch?
We would like to do that.
Normandale?
We would like to be.
Duluth?
Probably not.
How about Inver Hills?
I think we will make it.
Okay, so it looks like about half the teams or so would come. I'm not guaranteeing I can make it work, but I will try. On the other hand, those of you who said probably not, you can get back to me if you change your mind. But my expectation then is that you will fly sometime later, because hey, I bought you all this stuff. I want you to actually use it. And so we'll have to negotiate that, and it won't be just any time. It will have to be at some standard launch time, probably in the spring, that that I would be able to and willing to attend, but I wouldn't necessarily try to work for a special launch time. December would be a special launch. There is no standard launch scheduled for December. On the other hand, standard launches start in May for sure, and sometimes April. And so those of you who wouldn't fly at the end of the fall, I would expect to see you at some point in the spring, no later than the day of the Midwest competition, which is scheduled to be May 22nd, which is not actually a standard launch, that's a special launch. But there would be the May launch before that, the second weekend of May. And there might be a late April launch. And I would hope that you could make one of those times work. So keep that in mind, please. Thank you. Last question, anybody interested? Well, those of you who are going to get back to me, would you be interested in doing your checkout in person? Augsburg, I actually bring this up because last time, as in when Augsburg took lessons like this from me some years ago, Augsburg showed up in person. They didn't do a remote checkout. They came here and they did because it was just across the river. Augsburg, do you think you might even be interested in the in-person checkout?
Interested, yes. I'll have to check with my team.
Okay, the rest of you think about that. So not only when you would do it, but especially those of you who are here in town, would you be interested in coming here? I'm not saying you don't have to, you absolutely don't have to, but if you want to, that would be an option. So that's something I would like to hear when you make your decision, okay? Other questions, any questions from people?
What date exactly were you thinking the December launch?
It would be the first weekend of December. So either the 4th of December or the 5th of December, depending on the weather.
And where is it gonna be?
It'll be North Branch. That's where we were for the last launch. I think Kelly at least was there from Inver Hills.
Sounds
So-
good. Thank you.
That's where all the launches will be, whether it's December or not, it will be in North Branch. This is a regulated activity and therefore it has to be flown from a regulated field. Okay, so thanks all. And I may or may not bother to record the checkout interviews, but there won't, this will be the last all-team meeting and perhaps the last recording for this set of lessons. So again, thank you. And I will look forward to hearing back from the rest of you about when to try to schedule it. Give me, if you can, maybe 1 or 2 or 3 time slots. It's like, yeah, it could be Tuesday at 6:30 or 7:30 or 8:30. And I will then have a bit more flexibility when I say yes or no, especially if everybody asks for the same time slot, I can work around it. But I will make a decision as the requests come in. Okay, have a good night, everybody.
Thank you, Dr. Flaten.
Bye.
Thank you.
Thank you.
Hold on.
Thank you.
Toodles.
Hello.
Hi.
Hey, James. So please